A Nobel Prize-winning physicist just told us we have misunderstood the universe. Not in a philosophical sense, not in an abstract one. In the literal sense, our equations are wrong. And the most powerful telescope ever built just confirmed it. In this video, we're going to find out why the universe is expanding 8% faster than our best model predicts. Why James Webb found galaxies that had no business existing. And what all of this means for our understanding of reality itself. Because there is something in the space between the beginning and now. Something we have never directly observed. And it has been happening behind our backs for 14 billion years. It all starts with a number, the Hubble constant. It measures how fast the universe is expanding, right now, today, at this very second. By the early 2000s, scientists thought they had nailed it down. The war between rival camps of cosmologists seemed finally over. It wasn't. 67 or 73, who was right? Two teams, two methods, one universe. They get different answers, and neither one is wrong. First method, look back, way back. The ESA's Planck satellite spent 4.5 years mapping the cosmic microwave background, the faint afterglow of the Big Bang, emitted when the universe was just 380,000 years old. Result, 67 kilometers per second per megaparsec, meaning for every 3.26 million light years you look outward, galaxies are moving away 67 kilometers per second faster. Second method, measure the present directly. Adam Riess, Nobel Prize-winning physicist, and his team called JWST use what's known as the cosmic distance ladder. They start with pulsating stars called Cepheid variables. Their blinking rate reveals their true brightness. Compare that to how bright they look from Earth, and you get their distance. From there, they step out to Type 1a supernovae, stars that always explode with roughly the same peak brightness. They act as distance markers hundreds of millions of light years away. Riess's team got 73, not 67, 73A gap of 6 kilometers per second per megaparsec. That sounds small. It isn't. In a field where measurements are routinely precise to within 1%. An 8 to 9% gap between two independent methods is a scientific catastrophe. It changes the age of the universe, the size of the observable universe, and potentially the very nature of the dark energy that's been pushing everything apart. For years, scientists thought they had found the mistake. Cepheid variables tend to live in dense, dusty regions of galaxies. Hubble sometimes blended their light with that of neighboring stars. That made them look brighter than they really were. And the brighter a Cepheid appears, the closer it seems. The closer it seems, the higher the Hubble constant climbs. Fix the blending. The thinking went, and the tension disappears. So Riess pointed the James Webb Space Telescope at the same stars. Webb orbits 1.5 million kilometers from Earth. Its 6.5-meter gold-plated mirror collects infrared light with a precision that makes Hubble look like a pair of reading glasses. The anticipation in the scientific community was almost palpable. Some researchers were already drafting the announcement of the crisis's resolution. Webb confirmed Hubble's numbers, not approximately, almost exactly. In early 2024, the JWST team published in the Astrophysical Journal Letters. They had measured 1,000 Cepheids across 5 galaxies, stretching all the way out to NGC 5468, 130 million light years from Earth. 3 independent methods, all pointing to 73. Riess put it plainly, With the errors eliminated, what's left is the possibility that we have misunderstood the universe. But the Hubble tension was only the first problem. Almost as soon as Webb powered on, it started finding galaxies that had no business being there. Not small, dim, primitive galaxies, which is exactly what our standard model predicted at those distances. Massive ones. Galaxies seen as they existed just 500 to 700 million years after the Big Bang. Some of them rival the Milky Way in mass. A galaxy our own neighborhood took 13 billion years to build. Mike Boylan-Colchin at the University of Texas ran the numbers. To form galaxies that heavy, that fast, nearly every available atom in their surrounding dark matter halos would have had to convert into stars. Under normal conditions, that conversion rate sits around 10%. 90% of the gas simply never becomes anything. These galaxies were running at 100% efficiency, like a factory that somehow turns every scrap of raw material into finished product with zero waste. Physics doesn't work that way. The picture was partially clarified in 2024. Katherine Chworovsky showed that some of these apparently overmassive galaxies were being inflated optically by hungry black holes at their centers. The so-called little red dots. Their light was blending with the starlight of the galaxy itself, throwing off mass estimates. Once those cases were removed, the remaining galaxies broadly fit within the model. But not all of them. Roughly twice as many massive galaxies remained as the standard model expects. And in 2025, Webb found something else. A massive spiral galaxy, quickly nicknamed the Big Wheel, existing within the universe's first 2 billion years. Spiral structure takes time to develop. That kind of calm, ordered architecture in such a young universe has no explanation. There's a third crack in the model. Almost no one talks about it. It's called the S8 tension. It's about how clumpy the universe is. The standard model predicts a certain degree of clustering in the large-scale distribution of matter across space. When astronomers measure that clustering directly, they consistently find slightly less of it than the model expects. Riess called it the little sibling of the Hubble tension, less dramatic, but worth watching. And together, these two tensions point towards something fundamental: dark matter itself. It makes up roughly 27% of everything that exists, and we don't actually know what it is. Current models assume it's cold, heavy, slow-moving particles. But the elongated shapes of young galaxies observed by Webb match predictions from alternative models. Warm dark matter and wave dark matter, where the filaments of the universe's large-scale structure are smoother. If dark matter behaves differently than we assumed, everything shifts. The mass of galaxy clusters, the distribution of dwarf galaxies, the way gravity bends light around massive objects. You can't swap out the foundation of a building and expect the walls to stay where they are. So where does this leave us? The standard model isn't dead, not even close. It still explains the cosmic microwave background with extraordinary precision. It predicted the abundances of hydrogen and helium in the universe. It remains our best tool, but it's developing fractures that weren't there a decade ago. The Hubble tension refuses to go away. The early universe is producing galaxies that are bigger, more structured, and stranger than expected. Dark matter, 27% of the universe, may not be what we've been modeling for 25 years. And dark energy, 68% of the universe, remains a placeholder name for something we cannot identify, measure directly, or explain. Adam Riess was right from the start. We have misunderstood the universe. Not because we are incompetent, because we have reached the boundary of what our models can describe. Imagine assembling a jigsaw puzzle for decades. You think you can see the picture taking shape. And then you find a piece that doesn't fit anywhere. It doesn't mean the puzzle is wrong. It means the image on the box might not be the whole picture. New instruments are coming. NASA's Nancy Grace Roman Space Telescope will probe dark energy at an unprecedented scale. ESA's Euclid mission is already mapping the geometry of the universe across billions of light years. Gaia will calibrate Cepheid distances with geometric precision, removing another potential source of error. The next version of our map of the universe is being written right now. And it's going to be stranger and more beautiful than anything we've drawn so far. In a next video, we'll go to the heart of the problem: dark energy. What it's supposed to be, what the latest data is suggesting, and why some scientists now think it might not exist at all. Thanks for watching and subscribe so you don't miss the rest of the journey.